Okay, welcome to our fourth note set in our reverb unit. So unit 4, RVB for reverb. We just finished talking about convolution reverb or convolutional reverb. And that is one approach. And we're now going to move in towards into the second approach, which actually was developed earlier. I talked about why that was in one of the earlier note sets. And before we get into figuring out how to develop discrete time systems that will mimic reverb without relying on just implementing convolutional reverb based upon a measured impulse response, before we get into that, we need to nail down just what is reverb, what is it that we're trying to capture with this system. So I'm going to refer to that as perceptual concepts. And we've got one reading here by William Gardner, same Gardner who came up with the convolution reverb algorithm that we talked about in the previous note set. And I've alluded to this chapter 3 in this edited book before. We've drawn from this reference in the past. We're now looking at section 3.2 of that. And as I've said in the past, this book may be hard to get. I think it may still be available, but it's quite expensive. If you want this chapter, I would recommend that you contact a library. Just about any library should be able to get an interlibrary loan. So they'll either get this book for you that you can then borrow for a while, or alternatively, they might be able to just get a PDF of just that chapter for you. And then I'm also drawing some from section 6.1 of the DASP book written by Zolzer, but really it's this reference that I'm drawing the most from. So we've already talked about the fact that a room with a given sound source and a given listener position will have a particular impulse response. And we've looked at a caricature that looks like this. I think of this as, this isn't a real impulse response, but it helps us think about what's going on. We get these very discrete deltas, and we're looking at it in an amplitude that's in dB, so everything has been, absolute valued first. But we see some characteristics in this caricature that we want to be aware of. So one is that we get a direct term, and then and so this amount of delay here is irrelevant to us, because in a recording or in a live setting, we don't really need to mimic that aspect of it. But then the distance from the direct till when you get the first reflection, that's important. That has something to do with the size of the room. The bigger the room, the longer that is. And then we have this early echo section here, which I think I've said in an earlier note set that the duration of that early echo is on the order of 100 milliseconds or so. And there we see very sparse and discrete reflections. And so that's the early echoes. I say up here, well spaced in time. And that's where the directional information is coming from. Those echoes are coming off from a specific wall, and so you'll hear it coming from that direction. Then later we get into the late reverb, and we've talked about how that follows roughly a straight line on a dB vertical axis. That straight line characterizes the decay rate. And there we see things are very dense in time and diffuse in direction. You can't really hear direction there, because at that point, everything's just bouncing all around the room, and you're getting simultaneously sounds coming pretty much from all directions all at the same time. So the physics reason for this decay rate, which is a straight line on a dB plot. So that means it's decaying exponentially in non-dB. We can show that that is a characteristic of a room, a real room. And it's because once that sound field has become diffuse in the room, we can show that the amount of energy that you lose due to the absorption of the walls is proportional to the energy density of the sound field. And that's precisely what leads to an exponential kind of decay. So we can talk about the decay rate and characterize it that way. So bigger rooms are going to decay slower. Smaller rooms will decay faster. So let's talk about these early echoes. As I said, about the first 100 milliseconds after the direct arrives, for that first 100 milliseconds after the direct path arrives, you'll hear things that are very distinct, well spaced in time and directional echoes. And so these are what we call the early response or the early echoes. And we can think about each of these echoes, since we're thinking about them as distinct and separable, we can think about each one of those coming from some path that there was a distance that that wave traveled as it bounces between just a handful of walls at that point. And we take that distance and divide it by the speed of sound, and that will tell us the delay of that echo. Now we can also think about the amplitude of the echo after it reaches the listener. It's going to depend on how long it has traveled. So sound, just like other waveforms, will be attenuated based upon how far it's traveled. So there's well-known physics for that. So we know that the amplitude is inversely proportional to the square of the distance traveled. And then it also depends on all the different reflections. So however many wall hits it makes before it reaches the listener, you're going to have each one of those reflection reductions happening. So we think about a reflection coefficient. And if all those walls are about the same, we can model that with just a single number raised to a power. So that's the idea. So in reality, though, these absorption coefficients are not single numbers. They are frequency dependent. And so we might capture that with some sort of frequency dependent effect. So a frequency response of the path. And so this would be the frequency response of one particular echo, so from source to listener. And so each of the echoes that makes up the early echo section of the response would have one of these transfer functions. And so we've got the one thing out in front that has to do with how far it has propagated. So that's the amount of loss and the amount of delay due to just the length of the path. So we capture that, and that can also be frequency dependent. But then we have this is the frequency response of the j'th wall, and this set S is the set of all the walls that this particular echo has encountered on its path. So that just gives us a little way of thinking about how to model this, and we'll come back to this later in our notes. So I said that those early echoes also have directionality in them, and that's because they're very distinct, discrete reflections, and they're coming from very distinct, discrete, specific directions. So all the clues to source localization comes from these early echoes. So we might want to include something called the head-related transfer function, or HRTF. that has to do with the fact that if somebody is standing here, so, I'm thinking about looking down on top of a person's head, and those little things that I just drew are the ears, and suppose we have walls over here. So if something is coming from here, it gets a direct shot into the right ear, but it has to kind of diffract around the head to get into the other ear. So that the physics of that will say that some frequencies can do that more readily than other frequencies. So we should capture a left and right transfer function. And those would also depend upon the direction from which the response is coming. So there's not just one HRTF. There's one for each direction that the reflect is coming from. So we could just simply capture this in a much simpler way. We could capture it just with the time difference that it takes for the reflection to get to go to one ear versus to the other ear. So we could capture it with just that, together with not a frequency response, but just an intensity difference. So this interaural means between ears. And so these things could vary as a function of frequency, but we might just simplify it to saying it's independent of frequency. So we'll see as we go through this that sometimes we just make simplifications in order to make it a little easier to implement these things, or at least initially these simplifications are made. And then as time progresses on, people get motivated to include more and more of these details, or to say it another way, we get motivated to use fewer and fewer simplifications. There's another way of characterizing reverb, and that has to do with how long the reverb lasts. So now we're into the diffuse part, past the early echoes and into the actual reverberation part. And so the way we would talk about or measure the reverb time of a room would be the following. And these are two symbols that are used to characterize that. So it's a capital T, it's a time, so its units will be seconds. So the subscript R there is just to evoke reverb. And then the subscript 60 there is evoking this typical value of 60 dB that we'll talk about in just a second. So here's how historically the reverb time was defined and measured. So the idea is you go to a room, you put a source in the desired source position, you put a microphone in the desired listening position, and then from that source, typically a speaker, you put some steady state, or you put some noise there, some white noise perhaps. It might be some colored noise, but it's some sort of broad spectrum noise. And you let it run until you've reached steady state in the room. So at that point, early echoes are gone and everything just sounds like it's not changing per se. And then you turn it off, and that's where the counting starts. So once you turn it off, you're now going to be measuring at the listening position with a microphone. You are measuring the pressure of the sound, so the sound pressure level, but we're really interested in looking at the square of that, and we're going to plot that as a function of time. And that thing is called the energy decay curve. So it's a function of time, and it's going to decay down because we've turned the noise source off. And so now things are bouncing around, but eventually things decay down. And when that level drops 60 dB, not drops to 60 dB, but drops by 60 dB, that time is determined is declared to be the reverb time of that room. And you might do this many times and then average the results together. So you would have many reverb time measurements. They're all going to vary just a little bit. And so then you average those times and you would declare that's the reverb time of the room. And that's an important characterization of that room. And in fact, later we'll see that we will be designing our reverb algorithms to hit a specific desired reverb time. So that's how it's defined. Now, acousticians and physicists who study acoustics have experimentally shown that the reverb time depends on the volume of the room, so it's proportional to the volume. And then the A here, inversely proportional to A, that's the total absorption of the materials in the room. So that's not surprising. As the absorption goes up, the reverb time should go down. And as the volume goes up, the reverb time should go up. So that's the idea. Now, this absorption of the materials, it's not just frequency independent. So it can depend upon frequency. So if this thing starts depending on frequency, then this thing will also depend on frequency. So we should think about the reverb time as a function of frequency. So at certain frequencies, it's going to drop down by 60 to be at a different time rate than at other frequencies. But we've got this energy decay curve. That's just a function of time. So we're not able to see that. So we can come up with something else, another way of characterizing that. And this is just a different way of characterizing the EDC. And we're showing it as a function of time, just like we talked about up here. But instead of measuring with noise like we did up here, we basically find the impulse response. So H here is the impulse response of the room. We square it and then we integrate from t to infinity. So as t changes here, so as t grows longer, the integral here grows shorter. So we can see that at t equal to 0, we're getting the entire area underneath this squared curve. As t gets bigger, we get less and less area, so this thing is going to decay down. So that's just a more convenient way to measure the EDC. It doesn't help us address this yet. And this thing is called the Schroeder integral, and Schroeder is the guy whose work kicked off the discrete time simulation of reverb. So he's kind of like the father or the godfather of discrete time simulated reverb. But this is an important result, and it's called the Schroeder integral. So what are we going to do with that Schroeder integral? Well, based upon that idea, we can then take the EDC measured that way, and instead of putting it into the EDC Schroeder integral, we're going to take the impulse response that we can measure, and we now go back to Unit 1. We learned about a very nice way to measure the impulse response of a room. Nice dodecahedron speakers running exponentially swept sine waves, doing inverse filtering, and all that gives us a very nice measurement of H. And now instead of just doing this on H, we're going to do a bunch of different Schroeder integrals, one for each subband of frequency. So we're going to start with a measured impulse response, and then we're going to take that impulse response and run it through a bandpass filter. That breaks it into its frequency bands. Now, another way to think about this is we're going to compute the short time Fourier transform of the impulse response. And that's actually equivalent to running it through a bank of bandpass filters. One can show that theoretically. So if you go off into the theoretical characterizations of short-time Fourier transforms, you can find places where they think about the short-time Fourier transform as being the response of a bandpass filter, or a bank of bandpass filters. So either way, we get this thing that now depends on time and frequency. And so for each frequency that we're interested in, we compute the Schroeder integral. So we would take essentially the short time Fourier transform of the impulse response and now apply the Schroeder integral along the time axis for each of the short time Fourier transforms frequency bins. Either way we do that, we now get a function of time and frequency, and we can plot that in dB and then ask when does that decay by 60 dB. And so just so that we have a different name instead of the what we call the EDC here, or the energy decay curve, we're going to have a new name, which is the energy decay relief, or EDR. And we can see that's a function of time and frequency. And here's a nice plot right out of Gardner's chapter 3 in that book. And this is actually the EDR for the Boston Symphony Hall when it's occupied. So Boston Symphony Hall is a very famous concert hall. It's renowned to have really good acoustics. And this is a characterization of the reverb of that room. And we can see we've got time over here and we've got frequency over here. And this thing is, kind of normalized so that that level is 0 dB. So if we were to say, look at like 5 kilohertz, we're going to have to go start up here. And when we drop down by 60 dB, we say that's the T sub R at that frequency. Now, if we go at another frequency, we come down here like this. So at that same time, we're still way higher. So we'd have to go even longer until we hit that. So what we're seeing here is that the reverb time is longer at lower frequencies and shorter at higher frequencies, but it's not a simple relationship. And that might change from, one location, one room to another room. But that's important. We now know that the reverb time is a function of frequency, and this energy decay relief is something that we can use to think about how a particular room responds. So if you can measure the EDR for a room, that might allow you to give some insight to how you should model that room. And we'll cycle back to that in subsequent note sets. So now we want to get a feeling for some other nature of reverb. And this is the modal characterization of reverb. And this comes out of some theoretical studies that physicists and acousticians have done mathematically. So they start with some sort of idealized rectangular room, and they know what the materials are on the rooms, and so they can characterize that through some boundary conditions. And basically, we're setting up a wave equation, an acoustical wave equation. So that is a partial differential equation. And we can solve that for some simple idealized rectangular rooms with some particular absorption characteristics of the walls. And the solution of that is based upon some mathematical concepts that are basically like natural resonant frequencies of the room. And so engineers, when we think about filters, we think about a resonant peak and we think about resonance in that frequency response. But the physicists and the acousticians call those modes or normal modes, and they also call them eigenfrequencies. So an eigenfrequency is a frequency in the room where there is some natural resonance at that frequency. So if you were to excite that room with some broad spectrum noise, and then stop the noise, you would hear that frequency being accentuated. So that's the idea. And if we solve that under these conditions, we would get an equation for the frequencies at which these resonances occur. And so they depend on the dimensions of the room in meters in this equation, and the speed of sound in meters per second. So was it like 342 meters per second, something like that, if I remember right. And we have a whole bunch of these that are all indexed by integers from 0 out to infinity. And those integers show up here. So, we can see for the moment, let's just let these two be 0, so those go away. This square gets undone by the square root. So we can see that in that case, things are proportional to the dimension, in this case, in the z direction. And then we would have integer multiples of that. So those are all going to be harmonically related to each other. So that just helps us get a feeling for what these things look like. So acousticians use these normal modes to think about the behavior of the room's reverberation. So they think about that's what makes the reverb happen, is these modes, this resonance happening with sound bouncing back and forth in the room. And in fact, the first time I taught this course, I was in a room. I'll back up here and draw an above shot. It was a very narrow room. And these walls, so I was up here and the students were out here in seats. And these two walls had hard tile on them. So you could actually stand here, and if you clapped your hands, you would hear a very metallic kind of ringing sound. That was these natural resonances, these modes that you could literally hear in that room. It was not a room with very good acoustics, as we'll talk about later. So it's these resonances that when you turn the source off, they resonate, just like a parallel resonance in a circuit with a capacitor and inductor that are just swapping energy back and forth. The walls swap the energy back and forth, but each time they hit the wall or a wall, there is some damping, some loss of energy, and so that's how rapidly that dies out. Now, the study of this goes even further, and they can show that for this kind of room, and in fact, it pretty much holds for other not perfectly ideal rectangular rooms, the number of normal modes below some given frequency. So this is a function of frequency. It goes up as the cube of f, and we've got some constants out in front, but that's not the most important thing. The most important thing here is the dependency on f. So if we go up to a specific frequency and we say, how many modes lie below that frequency? This sets that number. Now we go up a little bit higher, and the number of modes that will be below where we're now at has gone up cubically. Okay, so now if we take the derivative of this, we can get an idea of the nodal or modal density. So this is change in node number of modes per frequency. And so, if we take the derivative of this is just a constant out in front. We're taking the derivative with respect to f. So the 3 comes down and cancels the 3. And now we get an f squared. And like I said, this result is generally not, well, generally reasonably accurate even for irregularly shaped rooms. So the density, how tightly packed those modes are in frequency, goes up quadratically. So it gets more and more dense as we go up. So the number of modes per unit bandwidth, or per hertz, grows as f squared. So here's a little plot that I made. I just said, let's imagine that we've got a reasonably sized concert hall. So about 19,000 square or cubed meters for that. And if we use this formula, we can say that below 10 kilohertz, there's like, more than 10 to the 9th normal modes. And if we look at 1 kilohertz, the density of modes around 1 kilohertz is 6,000 modes per hertz. So that's a spacing on the order of 2 times 10 to the minus 4 hertz per mode. So that's what I'm plotting here, the mode spacing. That's the in hertz spacing between modes. And you can see it's all really small numbers as we go up. And I'm only going up to 10 kilohertz. So these modes are very, very closely spaced. Even down at low frequencies, they're still pretty closely spaced. Everything is less than a hertz spaced. So we can also do a similar kind of thing. I skipped some of the steps here, but we can show a similar kind of density in the time domain. So if we're looking, remember we said the early echoes are fairly sparse, and then you get into the late reverb and it's just this thick, dense sea of echoes. Well, it gets thicker and thicker. So the density goes up as the square. And it's virtually the same kind of dependence. So that's kind of interesting. So this is what makes it hard to do this. We need to come up with discrete time methods that can not only create all these extremely closely spaced resonant peaks, modes, in the frequency response of the room, but also the impulse of the room should have very narrowly spaced spikes. Those would be all the echoes. And should get denser with time. And these should get denser as we go up higher in frequency. But this is particularly important. And that's the challenge. And we'll see that that's hard to do, but ultimately we will succeed. And you might know that. You have on your computer maybe some software that will let you mimic the reverb of a room, or maybe you have a little box that will do that for your guitar. I showed you a picture of the Big Sky reverb that can do this. So clearly someone has figured out how to do that, and that's what we'll be talking about in subsequent note sets. So let's take all this stuff and put it together, the things that we've learned. And again, we just scratched the surface of what physicists and acousticians have studied about this, but here's the idea. We've got the early response and the late response. They're very, very different in nature. So we're going to have to handle them separately. We'll have one thing that will model the early response and a different thing that will model the late response. So for the early response, those early echoes, we said that they are very distinct and quite separated compared to the density that happens in the late response. So we can think about an FIR filter, and we'll go into more detail so it'll be a little clearer what I'm talking about, but it'll be a sparse FIR filter. So in other words, we don't have to have a tap after every single delay. That's how we can implement this early response, and we'll see some of that. And we can even then say, well, we've learned that these different echoes might have different frequency responses, so we can handle that as well. And we can also handle some directionality. So we'll walk our way through, I think in the next note set, the methods by which we can accomplish these kinds of things. Then the late reverb, which will be not the next note set, but the one after that, we'll talk about, well, actually the two after the next one. So there's three more after this one, I believe. So the late reverb will model with IIR filters. That makes sense, right? Because things hit a wall and then hit another wall and then hit another wall. So it's like a signal being fed back to go back through an attenuation structure. So that's the idea. And this will allow us to mimic frequency-dependent decay and to establish that energy decay relief with a frequency-dependent reverb time. So all of that can be done. But at the same time, we need to be cognizant of the fact that there's all this high density resonant peaks in the frequency domain and high density echoes in the time domain. So we need to capture the ideas of those frequency maxima, and we also have to capture the density of the echoes in the time domain, as well as the fact that the density of the modes in the frequency domain, both of those go up quadratically. So we need to capture all that, and that's the challenge. So the early echo stuff, that's pretty straightforward to think about how to do it. It might be a little tricky to figure out what the exact absorption filters are to put in there and how to space the different taps coming out of the FIR filter. But the concept is pretty straightforward. It's just a matter of tweaking it to get what you want. But the late reverb, it's not at all initially clear how one should go about that to make sure you get enough echo density and you get enough mode density, while at the same time we don't want a reverb that's going to make it sound like we're suppressing certain regions of frequencies. Good acoustical spaces don't do that. They add this warmth, quote unquote, of the reverb without making the sound be filtered in its spectral representation. So that's the challenge, and we'll look at that in not the next note set, but the note set after that. We'll start looking at that. So just to give a little bit of idea here, so a room impulse response might have a number of samples on the order of 100K. So that would be, if we're talking about, 48 kilosamples per second, we're talking about a 2-second recording of this. That's not unusual or unrealistic for a room impulse response of a fairly sizable concert hall. So if we were to take that impulse response and try to model the whole thing with an FIR structure, that's just doing convolution reverb. So we might as well just take the measured room impulse response and put it into Gardner's algorithm and be done with it. But that's not what we're trying to do here. We're trying to give the user some knobs so that they can say, I don't want to have to go out and measure a particular room. I just want to be able to set a knob to say, I would like a reverb time of this, and I would like it to be highly directional, or whatever else you might set. I want it to sound like a spring reverb, or I want it to sound like a plate reverb, or I want it to literally sound like a real physical room. We don't want to have to go out and measure an impulse response for each of those characteristics. So implementing it as the whole thing as an FIR is really not what we want to do. But the early response, that's just the first 100 milliseconds or so, and that's something on the order of 5,000 samples, but they're also very sparse. right? We saw the picture where we see the early reflections are not very closely spaced together compared to the spacing in the actual late reverb response. So we may have 5,000 samples in that early part, but only a fraction of those samples of the impulse response will be a significant non-zero number. So we can use some sort of sparse FIR. So there will be many unit delays in a row where we're not tapping anything off from it. Then we have a tap. Then we might have many unit delays and another tap. Whereas for late reverb, hey, that sound is bouncing all around. It is just like we think about an IIR filter. The sound gets recycled back through something that mimics the reflection. And so that's a natural characterization for IIR. And also we know that IIRs are exactly what we need to make peaky resonant modes, right? FIRs, it's really hard to make a peaky mode. But IIR, just put a pole near the unit circle and you've got a peaky thing. That would be a normal mode, a resonance. And we can control the damping by putting that pole either closer or farther from the unit circle. So some sort of IIR makes a lot of sense for the late reverb. So here are two structures that are possible. And we'll talk in the next note set in more detail about each of these, but this is just a little bit to whet your appetite for this. So the first approach is to take the FIR that is chosen to model the early discrete reflections and would be a sparse FIR. And then we have an IIR that is modeling this late reverb, and you just put them in parallel. So basically the signal is going through each of them and then they get added together. Well, we don't want the late reverb to start until this is finished, till the early reverb is done. So we delay the signal by D samples before it hits the IIR so that this thing's response finishes just as the first thing comes out of that due to the signal being delayed. So that's the idea. And so then you can design these two things individually. The other approach kind of puts them in parallel, but also in series. So let's see what happens. We've got a signal X of N. It goes through the FIR and then comes over here and gets added in. So that's the same as this, although there is this additional delay. And we'll talk about that in just a little bit. But now instead of the signal going directly into the IIR, every little spike coming out of the FIR hits this. So basically the impulse response of this whole thing is many versions of that all interlaced. And that is a way of increasing the density out of this path. And that's good. We want an echo density that is very large density of echoes coming out of that. And that makes sense. And so these two delays are just there to try to make sure that this part coming out here doesn't start until the response that comes this way is done. And that makes sense. Maybe a small amount of overlap, but that's the idea. And we'll talk more about each of these structures in the next set of notes, and I hope that we will see you there.